Okay, well, some technical challenges today, but we'll get started. I have a computer. Let's see if I can get it to... Oh, well, I guess we won't have the computer demo. That's okay. All right, let's begin. All right, so as usual, I start with a problem every lecture whenever I can, and today's no exception. Nice number. It's composed of binary, which is good stuff. Zeros and ones, binary digits, and it's otherwise a word. So just like you would build words out of letters, alphabetic characters in some order. Order matters. It's pad is different than tab, and so on. So anyway, it's a string of zeros and ones, and this is relevant to computer scientists because you deal with packets of zeros and ones, bytes and words and so on. This is a binary string of length 32, 4 bytes long. Okay, so it's asking you if you picked a random one, how often, what's the probability that it would be nice? And it's nice if one of two conditions occurs. It's either begins with a 1, so its first digit, its leftmost digit is 1, or it ends with 2 zeros. So, what's the probability it's nice? Okay, so hopefully you've had a chance. I know it's only up here for about a minute. I'm just going to let you think about it for a few more seconds. Then we're going to do what we usually do in a situation like this where there's way more of you to participate than I can handle individually. We're going to vote. Okay, so we're going to vote just like we did last time. So please mentally pick one of these 5 responses. Got one? Ready? Okay, a couple more seconds. All right, it's voting time. All right, put your hands up nice and high so I can count them. And last time, most of you voted, which was great, and I hope that happens again. All right, so let's vote. Who thinks it's 1/8? One of you. All right, one of you. 3/8. Who thinks it's 3/8? Hands nice and high, please. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. All right. 3, 5/8. Nice and high, leave so I can count. A few latecomers to the game. 4, 3/4. Who thinks it's 3/4? Hands nice and high, please. 5 of you. And 7/8. 7/8. Who thinks it's 7/8? 2 of you. How many of you didn't vote? Not shy now, are you? Yeah. This is not a Canadian election. Okay, we expect you to vote. You can vote for more than one thing. I'll never know, right? I'll never know. Vote for all 5. You can't go wrong, right? Okay, well, this is going to be the way it's going to be. We are going to explore this. This is going to be a problem today, and I'm not going to tell you what the answer is quite yet. Okay, some of you know how to compute this thing right away, and we'll dig into a solution or two in a more mathematically rigorous way than what I'm going to show you first. And that is another technique that you can use if you have no intuition whatsoever. Okay, so if you have no mathematical acumen whatsoever, you have no intuition, you're a computer scientist, right? You can write a computer program that just does all the 2 to the 32 different things and just counts them all and divides, does the Laplacian thing, right? Divide by the total number of possibilities. So even if you have no idea what you're doing, you can still do this problem. Okay, so I had a Python program that I was going to run on the computer, but somehow my computer doesn't want to speak nice to the room today, so we're not going to do that, but I'm going to give you the Python program anyway. Okay, so if you had no intuition, Python, you could do the following loop. You could accumulate the total in something called result. You can run I for all I that goes from 0, which would be the smallest number, all the way up to 2 to the 32 minus 1. And in Python, a very fast way of writing that is to shift 1 32 places to the left. Of course, it won't go all the way up to 2 to the 32, which would actually be a 33-digit number. Okay, so this does what it's supposed to do. Then you test for the 2 conditions of niceness. One is if it ends in a double 0. You could divide by 4 and take its remainder, but you can just do bit munging operations and test for the last 2 digits, so that's a logical and. Or you can shift that should be an I to the right by 31 places, and if that happens to be a 1, then it's a nice number. Okay, so those are the 2 conditions. So if either of those 2 things are true, you increment result, and then you print the fraction over the total result, so float of result divided by 1 shifted 32 places to the left. Okay, so you can write this program and run it. It takes a little bit of time, and maybe it's better to write it in C. It'll take a little less time. Okay, but this is a brute force solution, and again, if you don't have any intuition, if you don't know the math behind this, you can come up with an answer that will match what we do a little bit later. Okay, so this is a brute force solution, and this is going to remind us a little bit later. There's a little foreshadowing to when we talk about sampling techniques. You could do something a little less complete, a little less, we're trying all the possible numbers and randomly pull numbers in this range, and it will eventually converge to the correct fraction. So this is going to be similar to sampling techniques, which we'll see later. Okay, but the brute force solution is just try everything. Okay, so try everything by exhaustion. Okay, so why am I introducing this problem to you now? Well, first I want you to think about something that we can apply the set techniques I'm going to show you as we go along, and we're eventually going to go back and do this later in the lecture, so hold tight until then. All right, let's set that aside for now. Okay, so this is, once again, this is our review section on set theory functions and combinatorics, a review for most of you from Mac 101. And we had a little intro lecture yesterday where we did some of those techniques and introduced some terms, and this is basically all we learned. This is definition of probability. It followed a Laplacian definition where you count the number of events divided by the number of possible ways event can occur divided by the total number of ways the experiment can end up. Okay, this equally likely assumption is a useful one for our purposes because it will allow us to do some calculations just using combinatorics. Okay, this is known as a uniform distribution where everything is equally likely. And we even defined these two sets. Okay, so event set, I've dubbed a capital E, and the number of possible outcomes is the sample space, and I've denoted that to be capital S. And when we put the bars around it, it means size of, and that's something we're going to define in short order. Okay, so the first thing we're going to do is set theory. All of these things are intertwined, and again, I'm not going to teach you all of the set theory stuff from Mac 101 because a lot of it isn't relevant for what we're doing. I'm going to try and get the stuff that you need for doing the probability stuff. Okay, so it's all within that context. But first, some definitions. What is a set? This is a pretty easy definition of set. There's nothing complicated about this. It's a collection of objects that doesn't have any order to it. There's a few little caveats. It talks about it being well defined. And so I mentioned this because there are some sets where it's not necessarily 100% this element A or whatever is in the set. It might be partially in the set, 50% inside the set, or 70%, or 25%, or whatever. Okay, so you can have some notions of partial inclusiveness. This is not what we're doing. Okay, so it's either in or it's out. There's no order to the elements inside the set, so it doesn't matter in what order you write the things. It's these two sets, for example, are equal, A, B, and B, A. And you can't have any duplicated items. So again, same sort of thing as partial inclusivity. You can't an element can't be 200% there. Okay, so two B's it doesn't have an effect. Okay, so it's actually the same as this one B. There are some other little nooks and crannies that you might have discussed in Mac 101, like Russell's paradox, and they talk a bit about infinity and what anyways, these are not things that we need. Okay, they're not things that are going to inform us for probabilities, so we're not going to talk about that. This will do. Okay, so something that you think is a set, you can list the objects, or if it's infinite, there's something that's connecting all the things. Okay, so anyway, the elements or members of the set are tied with this operator, this little E type of thing. So X belongs to A. X is a member of A. And if you look at the first set that I have in this example, A, and you can list out all the elements longhand, so red, orange, yellow, green, blue, indigo, violet, then we might say that blue is an element of A, so that would be fine. And we can also say that brown is not an element of A. Okay, so we just put a slash through the member symbol, just like we would put a slash through an equal sign to say it's not equal. Now, there's a useful thing that we're going to use a lot of, and that is something known as set builder notation. You can list out all the elements, but usually, there's something in common for these elements, and you can just write a descriptor. You can just say, this is what all the elements that should be in this set are. And this set A has a theme to it. What's the theme? Not just colors, but colors of the rainbow, yeah. So Roy G. Biv, right? Roy G. Biv? Yeah. Okay, so you can write out this set using the following notation. You can say it's all X, such that, that's what that bar means, X is a color of the rainbow. Okay, so X such that. So when we read this thing, some of you have seen colons or whatever. I'm just using bars, and you should do that too. Okay, so this reads as such that. And this initial, condition X such that, and then you list a bunch of predicates that, it's got to substitute for X, it's got to be true, set builder. And you're probably used to using that for your solution spaces for other purposes. Okay, so that's set builder notation, much more useful than listing things out manually one at a time. And our second example asks you to use set builder notation for B, the set of all even integers. How would you do that? Yeah, so all X, I'm just going to abbreviate it a little bit. Okay, all X such that X is equal to 2K, where K is an integer. Okay, good. Okay, so that's the definition of a set, pretty simple stuff. Size of a set, cardinality. This refers to a whole bunch of other possibilities for size. where they were looking into various degrees of infinity, and infinity is a valid size. Okay, so anyway, the cardinality, you put absolute value bars, but it's not ambiguous because you can't really take the absolute value of a set, right? It's not a number. Okay, so this notation says count everything that's in here. When it's something simple like Roy G. Biv, you just count the elements and you get 7. And in the case where it's infinite, you can write infinite or infinity. And as I mentioned, there are different degrees of infinity, and your Macam 101 instructor may have explored that. I know I do it when I'm teaching Macam 101. And this has been well studied. There are different degrees of infinity. This degree of infinity is known as countable. And there are other bigger infinities, like uncountable and so on. Okay, this is not a course in this, but we're going to mention countably infinite in some other definitions down the line. So just mentioning it here for completeness. Countable basically means it goes along the lines of the integers. Okay, so if you can sort of do 1, 2, 3, 4, 5, that kind of thing, or something that is a bijection to that, then it's countable. Anyway, there's a special symbol for this very special set that has nothing in it, and I know that doesn't seem very useful, but it does come up from time to time. It's known as the empty set. The notation with 2 squiggly brackets with nothing in there is valid, but I'm not going to use it very much. This is the symbol. It is a circle with a slash through it. I noticed that, and I warn people about this, I noticed that people write their zeros like this, and just be very careful. That's actually not a zero, it's an empty set. So you don't need to put slashes through your zeros. And in fact, you might be making a mistake if you do that. Okay, anyway, so this is the empty set. Next question for you. We have 2 sets here, this thing and this thing. Is there any difference between these 2 things? What do you think? The first one has a cardinality of 1. Why? Good. It's a set that has an element in there. It happens to be an empty set, and that's perfectly valid. You can have sets that contain basically whatever you want, and sometimes a set will contain a selection of sets. Okay, so that is a perfectly valid thing that contains one object. Okay, so yes, the size of the set containing the empty set is 1. Okay, so it's the set containing the empty set. Of course, the empty set has a cardinality of 0. Okay, so they are different. Just be careful about that. Okay, good. Before we get into some of the other operations, let me just refresh you on the sets that you use for numbers. Okay, and these symbols, actually this slide is the first time this slide has actually been correct. All the other ones I've used some kind of weird Z came out. These Zs are actually the right ones that you see in most textbooks. This is called blackboard bold. And if you're working on a blackboard, you can't just go over with the chalk all the time. So you write these 2 stripes. All of these things are in that blackboard bold type. So yay, I got it right. Okay, Z. Z is the set of integers. And Z plus, and you might see other variations of this, like Z greater than or equal to 0. That's different than Z plus. Z plus is all the positives. 0 is not signed. Okay, so 0 is not positive and it's not negative. Okay, so it is not in here. So this is the set of positives. Okay, and so it starts at 1 and counts upwards, whereas the set of integers is infinite in both directions. Right? So it goes 0, -1, -2, and all the way back down. What's n? Natural numbers, yeah. Okay, so this is interesting because if I asked some of you, you would say it starts at 1. If I asked some of you, you'd say it starts at 0. Same thing for mathematicians in the world. And if you, depending on what textbook you read, they'll start it at 0, they start at 1 for their own purpose. And, maybe some purposes are better than others. The one that we did in Macam 101, and I'm going to use that same notation here, starts at 0. So just be mindful that that's what we mean when we use it in this course, but other texts may differ. Q, what's Q? Rationals. What's that? What's in the set of rationals? Good, yeah. Okay, so it's the division of 2 integers. Okay, so we're going to write this using set builder notation. It's all x such that x is equal to, a divided by d, where we're dividing 2 integers. So a and d are integers, and I guess d is not 0 because we don't want the errors to end, right? And if you were, I don't know if you remember grade school, but they're on number line right in front of the room, big yellow thing back in my day anyway. And in grade school, they sort of started at 1, and then they sort of add 0 in there, so it starts at 0 and counts upwards. And then they show you negative numbers. Yes, indeed, your bank account can go negative, right? So they add negative numbers in there as well. The funny thing is that, fractions you learn about in grade 3 or 4, so they're sort of implicitly there, and it feels like if you were to plot those, you would end up getting, almost a solid line. It turns out there's a lot of gaping holes in there, okay? It is actually not dense. This set of rationals is actually countable. It's got the same infinite size as the integers, believe it or not, even though there's a lot more stuff in there that there isn't. The reals are dense, though, and that's what the real number set is about. We will not be doing a lot of stuff with reals through the course, although maybe at the end I'll talk about continuous stuff. We're going to be dealing with discrete land because we're computer scientists. But the set of reals is dense, and you deal with that a lot in calculus. We're not going to do a lot of that. And C is a set of complex numbers. We're not going to talk a lot about that either, but it's here for completeness. Okay, so this deals with the square root of -1, which is this impossible thing, possible, but you can do some math. You can do some pretty interesting math on that, and get some interesting results, actually, but we're not going to talk about that in this course. It's numbers of the form a plus bi, where a and b are reals. And I is the square root of -1. Anyway. We tend to deal with discrete things. Why? Because we build discrete machines, and that's just the number system that we tend to deal with. And I lost a page. Where did I lose a page? There it is. Found you. Can't escape me. All right. Okay, subset. Okay, so this is inclusion of one set inside another. If you have A as a subset of B, it's written with this sort of curvy thing. It is curved, it's not pointed, but it has some it has some similar flavor to x less than or equal to y, right? Where that is pointed, that's a less than with the bottom line under it means equality can happen. That's basically what's going on here. This line on the bottom means equality can happen. Anyway, A is a subset of B if everything that's in A is also in B. Okay. This can be drawn in what is known, this is our first of those pictures, and it's going to come up a great deal because these are very useful Venn diagram. Okay, and it's a depiction of the relationship between A and B. Here, if we were to say A is a subset of B and try to depict it on this diagram, what would I have to add to the diagram to make that relationship true? Say that again? A has to exist in B. What do I have to do to the diagram? Make B go around A. Okay, how do I do that? I see. I'll come back to that in a sec. Yeah. Remove the A part. You have to be a little bit more specific. Yeah, so the bit that's outside B, but in A, remove it. Can't really remove it. I've already printed it out, and so have you. But we can put a symbol in there that means sort of what you intend it to mean, that thing must be empty. Okay? So you had a good idea that maybe you could draw a different type of Venn diagram. We will draw these, and you should avail yourself of them if you think it's appropriate, where we draw circles inside circles. Okay, so all of A is contained all within B. Okay, so that's another way of doing the same thing. And these are isomorphic, assuming that this bit here doesn't exist anymore. Right? Anyway, equality is possible. Yeah. Equality is possible. If it's not possible, then we can write something called a proper subset. So this removes the line, just like you would remove the line, strict inequality, x less than y. You can have A as a proper subset of B, and you write it without the equality sign, right? Okay, so A is a proper subset of B means that there must be some separation between them, and I've already given you the punchline. There must be an x that's in B that's not in A. So we would depict this in the diagram by putting a thick dot and saying that is an item that is in there, that region, specifically that region. And we can do the same thing to this other diagram over here, and we can put x in that region. Good. Okay. Two sets A and B are considered equal if the elements of those sets are the same. Okay, seems pretty straightforward. You can also write this as A is a subset of B, and B is a subset of A. Okay, so A is wholly contained within B, and B is wholly contained within A, then A is equal to B, and vice versa. So it's an if and only if relationship. And that kind of makes sense, right? Because if you think about how equality works, just for the inequality thing up top here, if you had x less than or equal to y, and y is less than or equal to x, then they're sort of squeezed together, right? There's no other place where it can go, so x is equal to y. Okay, so it's the same idea, okay, but it deals with containment instead of inequality. Okay, we have a couple more things to do, well, one more thing to do, and then we'll go do the example at the beginning, okay? So not all notation and definitions, but we definitely need to get to this point, otherwise we're hooped. Okay, so we need some notation for these operators, okay? There are a couple more operators than this. This is going to be all that you see in the class. The other ones aren't as useful, okay? So this is it, okay? So there's complement, okay? So you're looking lovely today, not that kind of complement, Okay, and this one's spelled with an E in here instead of an I, and it means the negative space. Okay, so the stuff that's not in A, okay, but in the sample space. Okay, so all x such that x is not in A, and we write this with an A bar. I'm going to mention another notation that you might see where they put a little superscript C on the thing. I'm never going to use that, and you should never use that either, okay? I'm mentioning it so that when you read the reference texts that have this, you understand what's going on, but please use the bar, not the C. No, no primes either, okay? Don't confuse my TAs. Okay, anyway, A bar means all the things that are not in A. Then there's union and intersection. Okay, so this is, union is all the things that are in either set, so it's like an OR. Okay, so in A or in B, and we use the disjunction here. Okay, so this V thing is from Macam, logic stuff. Okay, so X is in A or X is in B. This one's AND. Okay, so that's intersect, it has to be in both. Okay, and the last one is subtraction. Set subtraction is you take A minus B, you take away all the things that are in B that are also in A, but you can't take away stuff that isn't already there. Okay, and the way that we write this is X is in A and X is not in B. Logically speaking, there's another alternate way of writing this, and that's A backslash B. Again, I'm never going to use that, and neither should you. Is it off the screen? Sorry. The screen needs to be lowered, I guess, a little bit. Okay, A backslash B, please don't use that. Okay, just be aware that some texts will use that. Okay, time for an example. A is a set of all evens. B is a set of all primes. Okay, well, it's not the set of all of them, okay, but it's a set of all of them in the sample space between 1 and 10. Okay, so just these 10 integers. A is a set of all the 5 even numbers that are there. B is a set of all the primes that are in there. Okay. A bar. Okay, what's A bar? All the odds. Good. Okay. And that feels right. All the not evens should be the odds. B bar. What's in? Non-primes, yeah. Okay, so you can list them out, right? So 1, 4, 6, 8, 9, 10. Okay, so this is, I'm glad no one said composite, although you might have been thinking of it. One is neither prime or composite. It's actually not part of the definition. Okay, so either one or has a non-trivial factor. A union B. Say that again? Good. A intersect B. Just two, yeah. So there's only one even prime, and that's certainly the case here. And A minus B. Yeah, good. 4, 6, 8, 10. You know, intuitively, it's sort of like, it's like A minus where A and B overlap, right? So the only thing that's missing is the 2. And you could have attacked this problem even using a Venn diagram, because it's small enough. So there's another style of Venn diagram. You know, this is A over here, this is B over here, okay, where you put the elements themselves in the diagram. I'm not going to put in dots or anything, because that would take too long, get too crowded. But, you know, 4 and 6 and 8 and 10 are over here. 2 is in the overlap between A and B. 3, 5, and 7 are over here. And, oh shoot, where's 1 and 9? Where do they go? Outside, yeah. So this is a region as well. Okay, so the entire thing here, this big rectangle, maybe I'll get the thick boy out here. Okay, so this entire rectangle, all the regions here comprise the set S. Okay, and you can use this diagram to figure out what you're looking at. Like if you wanted to do A union B, you could just list off all the elements you see inside the two regions, right? Sort of makes it visually easier. But you know, you don't have to do this if you see the thing right away. Okay, I'm going to pause for questions, and then we're going to do the example from the top of class. Any questions? Yeah? Good review? All right. Nice number time. Let's do it. Okay, so what do we do? Well, we set it up just like we had at the beginning, okay, with the definition of probability, right? You want to find the two sets and divide them, okay? What are the two sets? Okay, so first, let's get some words down here. Define the sample space and the event space. So S, the sample space, is all X. Okay, so X is a binary string of length 32. Okay, so this in our Venn diagram is S, basically. Okay, that big rectangle. A and B, to make it easier here, are going to be these two conditions. And we'll make A, B begin with a 1, and B be in two zeros. Okay, so all x such that x begins with 1, and B all x such that x ends with two zeros. Okay, so we would like to find the size of S, that's the sample space, that will be our denominator. And we have an OR relationship. Okay, so it either is in A or is in B. So what operation do we use for sets? Union, right? Union's got an OR built in. Okay, so our strategy now is to compute the size of S and the size of A union B and divide them. Okay, let's start with the size of S. What's the size of S? All right, too many people shouting out the answer. I want to ask one of you why. Okay, so I heard a bunch of correct answers, but I want to know why.
There's 32 blanks.
Good, yeah, so there's 32 blanks in the string, and each of them has two possibilities. So 2 times 2 times 2 times 2, 32 times. Okay, so the size of S is pretty easy. It's 2 to the 32, because each bit may be 0 or 1, which is two choices each. Now, I need another sheet. There we go. Okay, so A union B is going to take a little bit more time, because to do this, we can't just add the size of A to the size of B. And it would be easy to do that, because we'll find something similar, 2 to the 30 something, for each of those. And it would be nice if it did work out that way, but it doesn't. Why can't we just add those two things together? Now, one of them is A and B, and what's the problem? Yeah, so that region is counted twice. So if we bring out the highlighters here and sort of go, count everything that's in here once, and add all the things that are counted here once, we end up counting that middle thing twice. Okay, so I guess blue and pink make blue-pink. Okay, but yeah, so these two, that is counted twice. So because that would double count their overlap. Okay, so there is a way around this, and that is, we know that region is counted twice, so we could just subtract off whatever's in there as a matter of course. And this is known as inclusion-exclusion, which we have not defined, but you have seen it before. Okay, you saw it in Macro 101, so we're just going to get that in here because it follows our intuition. Okay, so the size of A union B equals the size of A plus the size of B minus the size of their intersect. And this is known as the inclusion-exclusion rule. Okay, we're ready to find the items that are in there. Okay, so first thing is we compute the size of A. Okay, size of A, so everything that begins with a 1. How many things are there that begin with a 1? Half of them, no, there's half of them, yeah, that's right, yeah. So half of them is how many? Sorry, we were dealing with numbers, sorry, I heard half and there's not half a number, no. How many is that? 2 to the 16, that's not half. Okay, I pointed at him, but that's okay. 2 to the 31, yeah, so the first digit is fixed, right? And the other ones have freedom, right? So it's 31 twos now. Okay, so first digit is fixed, one possibility. And the rest have two possibilities. And so that's 2 to the 31. And what about B? 2 to the 30. Why? Yeah, so the last two digits are fixed this time. But the other 30 are not. Okay, so we have 2 to the 30. And A intersect B. This is the case where both of these things occur, right? That's what intersect means. So it begins with a 1 and ends in two zeros. How many this time? To the 29, yeah. So 3 digits fixed, that leaves 29 not fixed. Good. So 3 digits, we'll use 3 digits fixed. Oh, sorry, thank you. I wish it auto-scrolled, but no luck. Okay, so those are the preliminaries, and we have A union B is, the size of that is the size of A plus the size of B minus the size of A intersect B. And that is, okay, so 2 to the 31 plus 2 to the 30 minus 2 to the 29. I could leave it like this, and then we could divide it by 2 to the 32 and maybe leave it like that, but really we want sort of a nice answer like what we started with, right? We have 5 choices that were simple fractions. I'd like to cancel as many 2 to the whatevers that we can later, and I think factoring is probably what we should do. The biggest factor we can take is 2 to the 29, and that will leave 2 squared, which is 4, 2 to the 1, which is 2, and 1 as the residual. So that'll give us 5 times 2 to the 29, and that is the total number of strings. So if you ran that program, the result would contain a number that was exactly that size, and then you would divide it by 2 to the 32, and you would get the same answer as we have here. The size of A union B over S is 5 times 2 to the 29 over 2 to the 32, which is 5 over 8. These are not lighting up as nicely as... That didn't improve anything. Oh well, we keep working on the technology a little bit. Hopefully that's readable enough. Okay. That's 2 pages worth of stuff. It must feel pretty good. Okay, solving a problem without having to write the computer program, probably a good idea. Okay, any questions about this? Yeah? Feel okay? Yeah? Okay, good. Okay, we are going to solve a lot of combinatorics problems, so I'm going to introduce this to you now. There's going to be a lot of overview slides like this where I sort of, I'm trying to talk into your ear and help you solve as many problems as possible. If you've done combinatorics before, and I suspect most of you have, you'll know that the game that you have to play is to read and interpret the word problem correctly and map it onto something that you've seen before, usually. Usually it fits one of several problem types, and the things that you need to figure out are, well, the following. Okay, first one is, does order matter? Okay, so often you're given a sequence like these are ordered pairs. Okay, so is the coordinate xy different than yx? And if it is, then order matters. Okay, so you should have more of a permutation type of approach. If it's a selection or a set, sets the order of the items doesn't matter, then order doesn't matter, and usually you're going to use some kind of combination, choose. Distinguishable objects, you are all distinguishable objects. I don't see any twins in here. You're even distinguishable objects even if you're twins. You're all unique and great snowflakes. Sometimes you're not, okay? So sometimes you care just about the quantity of things, and you don't care about anything else, like the amount of money you put in, the number of bananas you have, and so on. Okay, so you need to figure that out. And also, is repetition allowed? Are you allowed to receive more than one prize, or can you only receive at most? Okay, can you only be picked once? In our closing moments, we have seen a theme. One of the patterns happened a lot today. Okay, the number of ways to order R of n distinguishable objects with replacement. With replacement means like you have a bag you're selecting stuff out of. Okay, in this case, we selected zeros and ones, right? We selected a 0, we put it in the first position. The 0 goes back in the bag. We are allowed to repeat as many zeros as we want. Same thing with the 1. That's what with replacement means. How many different ways can we do that? Well, it ended up being 2 to the r. But in general, it's going to be n to the r, right? Because the blanks that we